Today we're going to take a look at section 7.2, which is operations on decimals. I don't expect us to quite finish today, but we'll get close. We'll be finishing up next time. So operations on decimals, the first operations we're going to start talking about are addition and subtraction. So as you'll remember that when you're working with decimals and adding and subtracting, the idea is to line up the decimal points and then add or subtract the same way that you would when you worked with whole numbers. And what I'd like to do is to talk about why this works from a fractional standpoint, because we've just talked about fractions, the whole chapter of it, okay? So if you take the 4 and 33/100ths, this is actually the same as 4, and I'm going to actually break it apart by place value specifically. This would be 3/10ths and then 3/100ths. And then the 3 and 26/100ths would be 2/10ths and 6/100ths. That's what it would be if we broke it apart by individual place value or written out in sort of the expanded base 10 form that we talked about last time. And then if you're looking for the pieces that are common or that are alike, the 4 and the 3 would be the 7. The 2 that are over 10 could be added because they have common denominators, so this would be 5/10. And then the 2 that are over 100 would be able to be added. 3/100 and 6/100 makes 9/100. So we would end up with 7 and 59/100ths. And that's why we line up the decimal points, is because we're actually adding place values that are common together by doing it in that fashion. All right, so let's look at an example of why we might want or need to add decimal values together. A stock's price dropped from $63.28 per share to $27.45 per share. What was the loss on a single share of this stock? So I titled this sort of part of what we're doing is addition or subtraction. Which one is this? Are we adding or are we subtracting? We're subtracting because it went down in value and we want to figure out how much that value went down. So I have 63 and 28/100ths, and I'm going to subtract 27 and 45/100ths. All right, so I lined up the decimal points, right? Got to have those lined up so that the place values actually match and are able to be subtracted. And if I start on the right-hand side, I'd have 8 minus 5 would give me the 3. What would I do about my 2 here in the 10ths column? I need to borrow from the place value over. And so if I take from the place value over, there's a 3 there. The 3 will become a 2. And then the 2 that's in my 10ths column will become a 12. And you might be surprised to learn that the word borrowing is sort of old vocab. You don't see it in most curriculums these days. You see the phrase regrouping. So what you're doing is you're borrowing from the 1. I know that's what you know you're doing, but you're taking $1 and you're turning it into 10 dimes. So the 10 dimes plus the 2 dimes are there is 12, so you have regrouped the money. And that's what they like to see used in current curriculums. So fun fact for the day. In the 10th column, we can subtract. 12 minus 4 now would give me 12 minus 4 would give me 8. There we go. I'll bring down my decimal point. And I have to regroup again because I can't take 7 away from 2. So I will take my 6 and turn it into a 5, and I will regroup so that my 2 is now a 12. 12 minus 7 would be 5, and 5 minus 2 would be 3. So this is $35.83. Couple of things to be aware of. Number one, anytime you've got units, they need to be present in the problem. So at the very end of the problem, I put my dollar sign back on. Okay, don't need it in the middle of the work unit, that's fine, but I need it at the end. Secondly, we are working on the how to do it kind of point of this. so I expect to see the how you did it. So I recognize you're welcome to grab your calculator, confirm that you didn't make any silly errors or whatever, that's fine. But if it's asking you to subtract these, it's actually wanting to see that you've actually done it. Okay, so there should be work involved. I should see the regrouping or the borrowing, whatever it is you're referring to, carrying if you're adding, that kind of stuff. All right, so that's addition and subtraction. Let's take a look at what happens with multiplication next. All right, so decimal operations. Multiply as with whole numbers, and then count the number of places after the decimal point in all factors, and this will be the number of places after the decimal point in your product. So if we do that on this problem, I have a 3 and a 7, and 3 times 7 is 21, okay? And then I count the number of decimal places. I've got 1 here, and I've got 1 here, so that's 2. So I need 2 digits after my decimal place here, and I would have this result. Okay, so that's the algorithm or the process that is written at the top of the page. So I'd like to show you why it works now. Again, from a fractional standpoint, I have 3 out of 10. That's what 3/10 means in decimal form too. And I have 7 out of 10 in decimal form written as a fraction. I would write it as 7 over 10. So if I were to multiply these, and I multiply across the top and across the bottom, I have 21 over 100. Do you see the hundredths there? That's why that's happening. The place values are getting multiplied, so I have that many place values in my answer. Do be careful if there's a 0 that gets used in that. So like if you had, we'll talk about this a little bit more later, but let's say you had 0.4 times 0.5, so 4 times 5 is 20. The 0 at the end counts in the 2 place values, so when I put my 2 decimals, it would look like this, which we of course recognize I can also write like this, where it looks like it's got 1 decimal, right? So the 0 counts in those place values that we're counting. All right, division. With division, we would make the divisor, that's the number we're dividing by, a whole number by moving the decimal point in the divisor and in the dividend an equal number of times, and then divide as with whole numbers. Okay, so again, let's do it with that algorithm, and then we'll explain how that works. So if I were setting this up as a division problem, it would look like this. Okay, what's being divided is underneath the division bar, and what's dividing by is on the outside. It says I need to make this a whole number on the outside, so I move the decimal point 1 over an equal number of times. So if it helps me, I'm going to rewrite it one time. This is now changed into 7.5 underneath and 5 on the outside because I've moved the decimal points 1 place. And then I would divide as normal. The decimal point would come straight up in my problem to the top of my bar. 5 will go into 7 one time. And again, I divide as though the decimal point's not affecting anything because it's just part of the answer already in the right location. And then 5 goes into 25 5 times, so I end up with 1.5. Okay, so that's the algorithm told me to do. But again, let's talk about why that would work. So I'm going to take this and write it as a fraction, like this. Okay, so I have the decimal point that is 75 hundredths divided by 5 tenths. And in essence, when I move the decimal point over here in this algorithm right here, what I'm really doing is I'm multiplying by 10. And we know from working with fractions that as long as we multiply the numerator and the denominator by the same quantity, it's a legal operation, right? It keeps the values the same. So in doing this, you can end up seeing there's that 7.5 divided by 5 that we get when we move the decimal points in the other sort of representation. Okay, so that's what's happening. When you're moving decimals, you're really multiplying by powers of 10. All right, So we're going to shift gears just a little bit in this section, and we're going to talk a little bit about scientific notation. Scientific notation is very useful in certain contexts. So first of all, the notation for it is that it's a times 10 to the n. The value for a is bigger than or equal to the number 1 and smaller than 10. It could be a decimal point, that's okay. Like the a could be 4.76, no problem. But it's between 1 and 10. And the n is an integer. Okay, so that's positive and negative whole numbers. So the exponent could be a 5 or a negative 5, but it can't be a 0.5 because 0.5 is not an integer. Okay, so exponents are positive, negative whole numbers, and then the base at the beginning, the a, can be any value between 1 and 10. Okay. So scientific notation. Can you guys think with me? When is scientific notation useful? Why would you want to use it? What kinds of things would you want to use it for?
Denoting a solution.
Okay, so any solution, like, or is there something specific about the solution that you're thinking of?
I'm meaning like chemicals.
Chemicals. Okay, but why would we use it there? It's not just because it says science in it, huh?
So you don't blow up.
Okay, but we could use those kind of computations potentially with our regular, representation of numbers. Brooke, do you have an idea?
Sometimes you can get numbers that are like 0.00259 or
Okay.
something like that, and you would want to move it and make it look smaller.
Yeah, okay, so you're talking about numbers that are very small numbers to begin with, right? That maybe have a lot of zeros before we ever get after a decimal point, before we ever get to some non-zero digits. Does that sound an accurate representation? Yeah, so if you're dealing with something really, really small, which would be your description as well, Bethian, is that if you're something really, really small, scientific numbers are really useful. There's one more place where scientific numbers are really useful.
Very large numbers.
That's right, Danielle. Really large numbers, like think about like distances in our solar system kind of stuff, really large numbers. So again, if you're talking about something in the billions and the trillions, it becomes really difficult to work with that number and do computations. But if you just convert it into scientific notation, computationally, it's a lot easier to work with. Maybe not as easy to sort of imagine how big or how small something is, but easier to compute with. And that's why scientific numbers are useful, is for those kinds of numbers. So they would not be useful for probably the money in your checking account, right? Probably not. And probably not for your student loan amount either, right? No. So we're talking, Demi's not sure. So we're talking either really, really, really tiny numbers or really, really large numbers for scientific notation. So let's talk a little bit about how we convert between these. I'm probably going to present this a little bit differently than maybe you've seen it presented before. To me, I think it's a little more user-friendly, and if you absolutely hate it and we want to talk about a different option with you and me individually, we can. So this is taking standard numerals, okay, that number that's really big or really small, and turning it into scientific notation. So you would move the decimal point to create a value between 1 and 10, count how many moves you made, and that number of moves you made, if the number was a large number to begin with, something really big, then that number of moves as a positive number is your exponent. If the number originally was a very small number to begin with, then the exponent would be negative of that many moves. Okay? So a lot of times when we talk about, or when textbooks talk about scientific notation, they use the words left and right. You move it left, you move it right, and that's okay. The problem is that it depends then, if you think about it from the left versus right, am I going into or out of scientific notation because the directions change? I'd rather have a description that works no matter which direction I'm going. So this one works. So let's take an example and I'll show you how. Okay, 298,000. Is it a big number or a small number? It's big. So the fact that this is a big number is going to mean that I have a positive exponent. Okay? That's the value of what we're doing. It's a positive exponent. Now, taking a look at the number 298,000, where would I place a decimal point within that number so that I get a number between 1 and 10? Between the 2 and the 9, exactly. So I'd have a 2, a decimal point, and then 9/8. You can leave off the zeros at the end. They're not valuable at all to us, okay? 2.98. What is valuable to us, as I continue in the problem, is I need to know what the exponent is, and the exponent relates to how many decimal points I'm away from where I began. And I don't care where you count, whether you count from the new location or from the old location, but the question is how many places does my decimal point shift? So yes, it is 5, good. And be careful when you're counting that you don't count the end points. That will sometimes happen, people will count as well. So you count the moves. This is 1 move, 2, 3, 4, and 5. So my exponent will be 10 to the 5th. And again, it's positive because the number is a large number. Okay? So let's say we want to go back the other direction. We start with something in scientific notation, and we want to turn it back into a standard numeral. Then we're going to move the decimal point, the number of places indicated by the exponent. And again, instead of worrying about left versus right, I'm going to worry about the positive or the negativeness of it. If it's positive, I'm going to end up with a large number at the end. And if it's negative, I'm going to end up with a small number at the end. Positive, large, negative, small. So we're going to do one. All right, so this exponent tells me, am I going to have a small or a large number? This will be a small number. So if I have 3.2, how am I going to have to move my decimal if I want the number to be smaller? To the left, correct? Yeah. So I'm just going to put a bunch of zeros here just as placeholders. I'm going to put more than I need just, to exaggerate the fact that I can. And we're going to move the decimal the number of places that my exponent says. So the exponent says 5, right? So we're going to move the decimal point 5 places. So here's 1, 2, 3, 4, 5. I didn't actually end up adding too many extra zeros, did I? Okay, so the 0 at the beginning, just one of them is fine, or you could even leave it off. And then I have 1, 2, 3, 4 zeros. 1, 2, 3, 4, and then the 3, 2. Okay? So again, negative exponent, small value when I'm done. All right, so I mentioned a moment ago that the nice thing about scientific notation really isn't even always in representing the digits or the numbers that I'm talking about, but it's in making computations with them, right? It's a lot easier to multiply single digits, numbers between 1 and 10, than numbers that are in the billions. It becomes quite tricky. So let me give you an example of a problem like that. So here is a problem that is in scientific notation to begin with, right? 8 times 10 to the 12th, 6 times 10 to the 15th, and I'm supposed to multiply the results together. Because multiplication is commutative, I can actually regroup these so that I multiply the 8 and the 6, and the 10 to the 12th and the 10 to the 15th, because multiplication is commutative and associative for that matter. So what is 8 times 6? 48. Awesome. Now 10 to the 12th, 10 to the 15th, we have exponent rules, which we learned in the last section of material, or last chapter of material. So what do I do with the 12 and the 15? I add them. So this would be times 10 to what power? 27th. I can't stop here though. Does anyone know why?
48.
Yeah, what's wrong with the 48? It's too big. This is not still in scientific notation because the 48 is bigger than 10. So what I need is I need it to be what number?
4.8.
Yeah, 4.8. But obviously if I change where the decimal is, it's going to change what the exponent is as well. Again, that number 48 was bigger than 10. Are you with me? So the exponent would also become bigger as a 28. If the exponent had been smaller than, or not the exponent, but the value at the beginning had smaller than 10, like let's say we did this, and for whatever reason at the end we had this as our answer. This is not my same problem. Please don't misunderstand. So again, I'd change it to a 4.8, but the number had been smaller to begin with, so my exponent would be smaller as well when I adjust. Okay? So that's what would happen on that. Awesome. All right, our last piece of information for today is we're going to talk about rounding and front-end estimation. All right, so estimation has lots of ways, there's lots of ways to estimate something. So one of the ways to estimate is by rounding, and that's probably the one you're most familiar with. So when we're rounding to the nearest blank, we find the location that we are told to round to, and then 0 to 4 rounds down, right? It becomes a 0 at the end. And then 5 to 9 rounds up. We increase the value at the end. We'll do an example here in a second, but while I'm still on this slide, let me contrast that to front-end estimation. Front-end estimation uses the first value or the first couple of values and rounds off. That is, it changes everything that is at the end to zeros. So when you use front-end estimation, basically you just keep the first digit or the first 2 digits and everything else becomes a 0. Okay? Obviously you can think that sometimes that means that it's going to be the same as rounding, right? Because sometimes that's what happened with rounding too. We just keep the value, we make things, at the end 0. But sometimes with rounding we actually round up, right? And that's not what front-end estimation would do. So let's see a couple of examples to these. All right, so here's our first value, 203 and 651 thousandths. And it's got some different examples of how we're going to do rounding. So we're rounding on these. So it says round to the nearest 100. So what number is in the hundreds place?
3.
The 2 is in the hundreds place, right here. So if I want this to round to the nearest 100, I identify the hundreds place, and then I look at the digit that follows it. It's a 0. So what would I do because that's a 0? I'd round down. So 203, 651, this number, what will it become? It'll become 200. What if that 0 were a 7? It would round up, and what would I get? We get 300, right? Okay, now not to be confused with, although obviously that's the whole point, part B, which says to the nearest hundredth. So what number is in the hundredths place? The 5. So be really careful when it's using, the language here that you're identifying the correct one. So there's a 5, and I go to the 1 afterwards. What does that 1 tell me that I'm going to do? Round down. So what will this number round to? 203 what? 0.65. Okay, everybody good so far? All right, the last one here says the nearest unit. So what do they mean by the word unit? The ones place, the whole value. They want whole values, no decimals, yeah. So what number is in the units place here? The 3. And if I look at the 6, what does the 6 then tell me? It tells me I'm going to round up. So what will this number become? Yeah, 204. The 3 will actually become a 4. All right. So I'd like to do the next example where we actually are able to contrast the difference between the rounding methods and the rounding method and the estimation method with front-end estimation. So you're going to have some questions in your homework that are going to look a lot like this, where they say use A, rounding, and B, front-end estimation to estimate the following. So let's just talk about part A here first. Use rounding. So what are we going to do? What are we rounding it to? What's that?
89.5.
Maybe.
Do we get to choose?
We get to choose, yeah. So we don't have a place value given to us. You assumed the 10th place, right? When I looked at that 89.47, I'd like to round to the tens place myself, because that's almost $90. And probably for the purposes, and especially if we're working with money, that'd be close enough. So you get to pick, okay? So you get to pick, do I want to round to the tens place? Do I want to round to the hundredths place? Do I want to round to the tenths place? Whatever's going on in your problem, you get to pick. So starting on part A, and we actually are going to have to pick for both rounding and for the front-end estimation. So let's do the tens place so that we can talk about it in contrast. So if I'm rounding in the tens place, what we would want to do is to round, okay, it does not benefit you to do all the work with all the decimals and then round. You guys realize that, right? Like the benefit of rounding is to do it at the beginning so that the computation is easier. Okay, good. So 89 and 47 hundredths would become what if I rounded to the tens place? It would be 90. Okay, so my 8 is in the tens place, and the 9 here would make the 8 that's in the tens place round up, so I have 90. How about the 32 and 16 hundredths? Yeah, the 3 will stay as 30 because the 2 that follows it is the tens place. So 90 minus 30 would be 60. Thank you. Okay, cool. So we have 60. Then if I do part B, where I do front-end estimation, let's look at what front-end estimation looks like. So front-end estimation can be very useful. Certainly very quick, and that part's kind of nice. But what front-end estimation does, and we're going to do it still with one decimal place, or not one decimal place, one digit, the tens digit, is that it takes the first digit and it simply makes everything else 0. So 89 and 47 hundredths would actually just be 80. That's front-end estimation. You keep the first digit 0, everything else after it out. And then your 32 with your change would still be 30. Because you keep the 3 and you 0 everything else out. So 80 minus 30 would be 50. So clearly, those two estimates aren't the same. They're both estimates. They're both reasonable, but they're found in different ways. Okay? Part C says that we're actually going to, well, it doesn't say it's part C, but it does ask. It says, then perform the computations to see how close your estimates are. So we're going to actually subtract these. I'll call it part C. Okay, I lined up my decimal points, right? So what would I subtract first? Yeah, the first on the far right, 7 minus 6 would be 1. And then 3. 4 minus 1 is 3. And bring down my decimal point. 9 minus 2 is 7, and 8 minus 3 would be 5. 57.31. It may be tempting because it sort of looks like decimal points where there's money here to put a money sign on, but there's no money symbol on this, right? There's no dollar amount actually here, so we're good. That was simply part C. Okay. Let me just talk briefly about number 7, and then we'll wait to do it next time because it's a little bit of a lengthy problem. The problem is this. A student tries to calculate 0.999 to the 10,000 on a calculator and finds the answer to be 4.5173346 times 10 to the negative 5th. Okay, so first of all, what kind of a number is that? It's in scientific notation. Is it large or small? It's a small number. So this number is almost 0, right? It's very small. But the student wonders how it could be that a number like 0.999, which is so close to 1, when it's raised to a power, could result in a number so close to 0. So do you understand the student's question? If I raise 1 to a power, 1 to the 10th, 1 to 100th, 1 to the 1000th, I always get back the number 1, right? So how is it that I can take a number that's almost 1? I mean, let's be honest. If you go to the gas station and you see those 3 nines, you pretend like it's not even there, right? In fact, you don't pretend in the right way, probably. You ignore the third one and you just like zero it out. But you act like if you saw 99 cents in the grocery store to pay for something, in your mind you would automatically think it's going to cost me a dollar. You don't think 99 cents, not really, right? It's a dollar. It's practically one. So how is this number that's practically one, when it's raised to a power, become zero or nearly zero? So do you understand the student's question? Okay, so we're going to explore how this is working and why it's happening next class period. We will finish this section next class period, so there's no homework for this evening. And we will also move on to 7.3 just because I want to make sure, we've only got one day scheduled for 7.3, so I want to make sure that we actually get that on time, okay? All right, see you guys next time.